Alright, let's take a look at the next example here. So in this particular one, as we've been doing in this entire series, we're going to be taking a function. In this case it's a quadratic polynomial that we're raising to the sixth power, and we want to take its derivative, its first derivative, and also the second derivative. Now we could expand this out to the sixth power, but that's not going to be the best thing to do. If you think about this, what's the basic structure? Anytime you do a derivative, you want to think about the structure of the function. So notice here you would square first, multiply by 5, multiply the input by 3, sum those up, and then raise to the sixth power. So when you're taking the derivative, okay, how should we think about this? Well, the derivative then is, of course, the derivative of what we have. You want to think of this as the derivative of something to the sixth power, where that something is what we substitute in. I'd usually use the letter u. So where u is that more complicated base. So notice again, the last thing done in evaluating the function, is going to be the thing that you use, the power that the rule that you're going to use. So the last thing is raising to the sixth power. We're going to use the power rule. But to do that, we need to do a substitution. Okay, so we're taking the derivative of that. Okay, well, that's something we know how to do. That is the derivative of this. U to the sixth is just 6 u to the 1 less, which is the fifth power. But then you always have the derivative of the u when you do a substitution, and you multiply that by the original part. So remember, the chain rule says that we are going to multiply rates together. Now when I substitute back in what the u is here, then we take this derivative of this polynomial. That's not too hard. 2 times 5 is 10. Power goes down to 1. Derivative of the 3x is the 3. And the derivative of the 2 is 0. So that part goes away. So there's our answer. If we just plug in back what u is here in place of the u here, and we could leave it like that. I think I'm going to write this one in the front. Doesn't really matter. And so there is the formula for the first derivative. Okay, how about the second derivative? Alright, now this is going to get a little bit more complicated for the second derivative, because we're going to need to apply the product rule on this. Okay, because you see, you still have this to u to a power with the same u, but we have another part here. Now first of all, we can use the constant multiple rule, and we know that 6 times this the derivative of this whole part in here. Now, in fact, let me rewrite it like this. Okay, so you see what I've done? I've done the same substitution we used before. So this is u to the fifth. I'm going to leave this 10x plus 3, bring the 6 out front of the derivative sign. So it's like that. Okay, now for this derivative, I'm going to, what's inside this bracket, I'm going to apply the product rule. So it's the first times the derivative of the second plus the second, which I'm going to just leave as u to the fifth for the moment, times the derivative of the first. Okay, now let's see. Let's do this last part. It's the easiest. Derivative of 10x plus 3 is just 10, and we've done this derivative, so that goes away. Now the derivative of u to the fifth is 5u to the fourth, but then we have the derivative of the u. Okay, this u again is this part right here, so we need that derivative. I'm going to go ahead and write this as 10u to the fifth and pull the 10 in front of the 5 there. And I'm going to bring the 5 in front here. Okay. So far so good. Okay, the derivative of this part we get from the chain rule. That's pretty easy. We've done this already. It's 10x plus 3. Okay, now let's see if I can do any factoring or cleaning up of this before I switch back, get rid of those last u's. If you notice, these both have a u to the fourth. So the smallest power on the u is that. So I can actually bring the u to the fourth out front, and that just makes this one a u to the first power. And the first one, this part that had a u, just went away altogether. They both also have a 5, which I can put with this 6 and make 30 if I get rid of this 5 and make this one go down to 2. And these two are the same factor, so I might as well write that with a power 2. Alright, that cleans it up a bit. Now, again, let's go back here, and this was the u, remember? See, up there? So, if I can put that in place of the u here and here, we're in good shape. Now, that's not too bad of a form. However, I think I can simplify what's inside this bracket a bit. Okay, first of all, multiply the 2 out. So this makes this a 10, a 6, and a 4, and that gets rid of that parentheses and the 2. Now I can square this one out as well. So this is a 10x squared is 100x squared, plus, multiply and double them, that's 10x times 3x is 30x doubled is 60x, and then the last term is 9. So that's what's going to happen when we square that out. Now I should be able to take this and combine some like terms here. 10x squared plus the 100x squared is 110x squared. 60x plus 6x is 66x. And 9 plus 4 is 13. In fact, let's take that instead of those little square brackets. Let's use a parentheses around that. And then it would be nice if I could factor that. I would factor it out. I'm not going to try to take the time to see if it'll factor or not. But that is the second derivative. So we had to use the product rule and a substitution, so the chain rule there. So the first derivative was a pretty straightforward just chain rule problem. Substitute in, power rule, chain rule, said we also had the derivative of this polynomial. Then the expression got a little more complicated than the original function, so when we had to do the derivative the next time, we used the constant multiple rule first, then we used the product rule right here, and we of course did some substitution here, so we had to use the chain rule on this part, use the power rule in conjunction with the chain rule. This part was pretty just a derivative of linear. Then we have the derivative of that quadratic. So polynomial, not too bad there. And then we did a little factoring with our distributive property, common factor factoring. Then we substituted back in what u was, and then we cleaned this up here a little bit by using the distributive property to multiply this all out, combine like terms, and voila, we have the final answer. Now, so let's go back up here to f prime of x. Let's go back to f of x first. And we want to find the tangent line to f of x when x is 1. So the first thing we're going to have to do is find out what the point is. So if we put the point x is 1 in here, we'll be able to come up with the corresponding y. So 1 squared is 1 times 5 is 5, 3 times 1 is 3, 5 plus 3 plus 2 is 10, 10 to the 6th is 1 million. So 1 comma 1 million is the point we're talking about. Okay, when I graph this, I'm going to have to go way up there, aren't I? Okay, now what's the derivative at that point? This will be the slope of our tangent line. So if we take this, looks like it may be pretty steep there too. Let's see. We put in a 1 here, then we put in a 1 here, here, and here. Let's see how this works out. Let's see, 10 times 1 is 10, plus 3 is 13. Again, this is the same computation we did before. This is 1, this is 1, so this is 10, but it's to the 5th power this time. Okay, so let's do 6 times 13, 78 I believe. And then we got times 10 to the 5th, so that's 5 zeros appended to this. So 7,800,000 is the derivative. That's the 7,800,000 is the derivative. So that's the slope of the tangent line. So on any kind of normal scale, this is going to look almost vertical. But let's take a look at the tangent line now. Okay, it's this derivative, which is the slope, and then we have x minus the x coordinate of 1, plus we have the y coordinate at 1 right there, and that is the formula for the tangent line. Okay, let's do some graphing. Okay, that's the leftover from the last time. Now, I know just by the fact that the point of tangency is goes up 1,000,000 for the y's, I'm going to need to go probably way out for the grid range. So let me just start by going top 10 to the power 6 is 1,000,000. Let's go 10 to the, at least 10 to the 7th, and then maybe we'll go down that far. Minus 10 to the 7th. And let's just start with negative 10 to 10 on the y, on the x's, and let's just see what happens. Okay, we may have to adjust this window. Okay, so the original function was y equals parentheses 5x squared plus 3x plus 2 to the power 6. Okay. looks like this is going, here's 4, looks like here's 1, so there's the 0.1 comma 1 million right there. Okay, so there's our original function, and we may change our window a little bit in a minute, but let's start with that. Then our derivative is y equals 6 parentheses 10x plus 3 parentheses 5x squared plus 3x plus 2 to the power of 5. So there's the derivative. And the second derivative was y equals 30 parentheses 5x squared plus 3x plus 2 to the power 4, and then times 110x squared plus 66x plus 13. And there's the second derivative. And the tangent line, let's see, it was y equals 7, 8, and then 5 zeros times x minus 1 plus 1 million, 1 with 6 zeros. Okay, let's get that. Let's make the tangent line green, let's say. Alright, so there we got it. Let's see if we can maybe change our grid range just a little bit. Let's see, I don't think we need to go nearly as far out to the left or right. So let's just go -3 to 3 to find some interesting part of this. And let's just go negative, let's see what happens if we just go -1 million. And then maybe go 2 million up here. Yeah, that's not bad. We could go with that, I guess. And so we can see what this looks like. Now there's a good big picture where we can see this. Now it might be that we'd like to go ahead and get a closer up picture as well. So let's maybe take a look at a closer up picture in just a minute. But let's get this one pasted over here. But sometimes it happens that one graph doesn't show everything. So we see a good big global picture, but looks like there may be some detail that's missing right in here. We may not actually be able to see the tangent line on where I want to zoom in. But let's maybe leave the x's alone, or maybe even come in a little bit, mainly between -1 and 1 mainly, and look at what happens there, but come in quite a bit on the y's. -1,000 to 1,000. Yeah, we can see a little detail, a little more detail there of some interesting things. So from here you see that it looks like the original function is concave up the whole way, and the second derivative is positive. The derivative function is increasing the whole way, which makes the second derivative positive, and the original function concave up. The second derivative crosses the first derivative crosses the x-axis right here, so that's where the minimum occurs on the original blue function. The derivative is negative over here. That's when the original function is decreasing. The derivative is positive. To the right of that point was where the original function is increasing. The tangent line looked right when we looked at the other picture. Notice that we have where the second derivative is never 0, so there's no change in concavity here of the original function. It's concave up the entire time. So maybe there's a closer up picture that shows a little bit more detail about what it looks like in that part. So sometimes it takes more than one graph to get a good idea of what's going on there. Alright, so we've got a couple of exponential functions coming up and some other functions down here. Again, look at this next one and then come back after you've done and watch the next video to see the solutions to it.